Assalamu alaikum and welcome back. Today we have lecture number 10, and as you know from the previous lecture we are discussing the second part of the course where we discuss which is systems, right? So we are discussing about different properties of the system, and this lecture we are going to discuss the linearity property of the system. So a system is said to be linear if the following two conditions are satisfied, right? And these are the superposition and homogeneity or the scaling, right? So superposition is defined as if the input x1t produces, you understand superposition is kind of addition, right? So if x1 of t produces y1 of t, you understand by we also represents the arrow, right? So to the right left side of the arrow is the input signal, and the right side of the arrow indicates the output signal. So that means there is a system involved. Okay, so that means if we give it x1 of t and it produces or it generates y1 of t, and if we give it x2 of t and it produces y2 of t, so it will hold the property of superposition if we sum the input, that is x1 of t plus x2 of t, and it produces the y of t, such that y of t equals to y1 of t plus y2 of t, right? So in such a case we say the superposition property holds. Similar is the case for the discrete time system, that we have x1 of n input and it produces y1 and so on, right? So I hope similar arguments hold, so you can say similar things about the discrete time case, right? So graphically we can say this whole procedure, which is the superposition, right? So superposition we can represent graphically as here shown in the figure on the right side. Okay, so if you look at the figure, it's right, we are just adding this outputs of the two system. You can observe here that in the top figure, right? Okay, let me mark. So in the top figure here we have the inputs. Okay, we have the system, we find the output, and then we sum the output. Okay, so in the second figure we have the inputs. Okay, we sum the input and then we apply some system and we produce the output. Okay, so if this system holds the property of superposition, then in both cases, whether we sum the signal and whether we produce the outputs, right, like in the top figure we produce the outputs like here. Okay, we produce the output and then we sum. Okay, that means input system output, input system output, and then we sum the outputs. Or if we sum the inputs and then find the output, if the system is linear, in both the cases we should get the same output, same results, right? So if the system produces the same results, then we say the system holds the property of the superposition, right? So remember that there are two conditions for a system to be linear. The first one is superposition, and the second we discuss here is the homogeneity or the scaling. So what is homogeneity or scaling? So I think you have understanding of the scaling, because we have done this in while we were talking about the operations on the dependent variable, and we also discussed about it when we were talking about the operations on independent variable, right? So for example, we have input x1 of t, and you understand by arrow means some processing. So the left side shows the input signal and the right side shows the output signal. So if you have, so x1 of t produces y1 of t. Now if I scale x1 of t by a factor of a, the y should also be scaled by the same factor. If this happens, then we say that the system holds the property of homogeneity or scaling, right? It also says if the input is 0, out should also must also be 0. Like for example, if I multiply, I scale the input by a factor of 0, so output should also be scaled by a factor of 0. So that means 0 input produces 0 output, right? Now because both the conditions are a must for a system to be linear, so we can also say for a system to be linear, 0 input must produce 0 output, right? 0 input must produce 0 output. If this is not the case, then we say the system is not linear, right? So similar arguments apply to the discrete time case also. You see that you have system x1 of n, and you understand how you identify whether it's a discrete or continuous. So you understand, you identify it from the parentheses, right? So if we have parentheses like we have here, so it means a continuous time system, right? If we have a square bracket like here, so that means it will be right. And also the variable, the independent variable. So in case of continuous time system, the independent variable is t, and it has real values or continuous values, whereas in case of discrete time system, the independent the discrete time signal, so the independent variable is n, and it has integer values, right? So I hope that's clear to you, that if both of these properties, that is superposition and homogeneity, if they are satisfied by any system, then such a system will be called the linear system. Okay. So mathematically, we can combine the two properties, because x of t, like we wrote x1 of t, right? x1 of t and plus x2 of t, right? So we just did for two example. Input signal can have many I mean many terms, so we can say okay, blah blah blah. Okay, so similarly we scale the individual signal by if you recall, by a and b. So if I write, okay, the first signal scaled by amount of a1, then the second is scaled by a2, and so on, right? So if I write it in summation form, so it will be something like this, right? You understand, because if I open this, then I running from 1 up to n, so that means I have this type of equations you have seen. So we can say, okay, summation, you understand that terms are going to be added, so we can say for I running 1 up to n, so that means it will start at 1, so a1 x1 t, then because there is summation involved, then we write plus, and then we say a2 x2 a3, right, up to n. Okay, so similarly, like we said, that if x1 of t and x2 of t produces x1 of t produces y1 of t, and x2 of t produces y2 of t, so summing and scaling will result into y, which should be equal to the a times x1 of t, a times a1 times y1 of t plus a2 times y2 of t. So similarly mathematically we can write it, so because we understand that we can also represent the system by the operator h, right? So we also represent, I mean, by the operator, because system is performing by one of the definition we said system is performing some operation on the signal which results in a new production of new signal. Okay, so we just write like this: y of t equals to h x of t, right? Now x of t is summation of these sig parts, so we can say that h into, I hope this is clear to you, right? So I running from this, and you can write h, because we say that the system is linear. So if the system is linear, then we can write it right. So what I did is just I expand the operation, the summation, okay? And because the operation is because the system is linear, so summing this whole and applying the system, because on the previous slide I have shown you that it's same, that you sum the signal and you produce the output, or you produce the output for individual and then you sum it, so it must result into same. So that is what we call it, the superposition, right? So superposition property we are applying here again. So instead of applying this the system on the whole summation of the signal, we are applying it on individual, right? So we can say h a1 x1 of t plus h a2 x2 of t, and so on. Again, from the property of the scaling, because we said if x1 of t produces y1 of t, right? Let me just, okay, so if x1 of t produces y1 of t, okay, so that means if I scale x1 by a, this should also be scaled by the same amount. So that is what we are doing here, because we say h a x1 of t, so we can take out a here. Okay, so this is your you see y1 of t, right? And why y1 of t? Because we have input signal x1 of t and we are applying some operation on it which will result into y, because this is x1, so we call it y1. This is x2, so we call it x2, and so on, right? So that means we can replace h xit by yit, because this is what results from this signal, right? This signal, and this is the operation the system is performing, and that's the output you get. So you understand that when our system performs some operation on the signal, we have some output. Okay, so that means in the summation form this can be, right? You can also write it like this. You say, okay, a, and because h x1 of t should be equal to y1 of t, right, plus a2, okay, and you have h x2 of t, so it will be y2 of t, okay, and so on. That means for all up to an, right? So this thing in summation form can be written like this. So you have, okay, similarly for the discrete time case, you can go and you can derive the expression. Okay, so it will result into this thing. Okay, so that's quite straightforward. Okay, so to test whether a given system is linear or non-linear, you simply check the two conditions. First one is the superposition. You give it an input and you find the output, then you give it some different output input, and you get a different output, right? In the second step, you sum the inputs and you find the output. If these output and the output earlier you got are equal, then that means they hold the property of superposition. Okay, and similarly, so if they hold this property, then we say the system has superposition property, right? Then the second property, which is also must, is the scaling property. So you scale the input and you check whether the output is also scaled by the same factor. If it is, then you say the system is linear. If any of these properties are violated or not satisfied, then we cannot call such a system as linear system. Okay, we'll talk about more about we'll talk more about the linear system in the coming chapter. Okay, so let's have a numerical. Okay, so for example, we have two systems, rather we have four examples, right? So maybe one or two I'll solve, and the rest I might leave it to you. Okay, so so let's take these two examples. Okay, and we say we need to check whether the given system is linear or it is non-linear, right? So that's quite straightforward. If you look at the equation quite carefully, you will observe what is the system doing in part 1 here. So what it is doing, it is just scaling the input signal by a factor of x of by a factor of t, right? So if I give it x1 of t, what it will do, it will produce x1 of t, so it will produce y1 of t, right? And what will be the value of y1 of t, because we are given that the equation says whatever you give it to the system, the output is t times the original system, right? So that means t x1 of t I should get at the output. Okay, because when we were defining the superposition and scaling property, at that time we was just taking the generalized, because we didn't know. We just say okay, x1 of t produces y1 of t. But now, because we are given the exact relationship, so we can tell what will actually y1 of t will be. Okay, so we say okay, now I check if have a selection or something clear. Okay, so this produces this one, then we say okay, let me copy this. I think it will be easy. Cannot. Anyway, so if we have y2 of t, what it will result, it will result into y2 of t. Okay, x2 of t results into y2 of t, and y2 of t will be equal to t x1 of t. Okay, now I say we have a third input, right? Let we have x3 of t such that x3 of t equals to the superposition and scale version of the these signals. So okay, I say okay, x3 of t equals to a1, or not a1, in fact just a a x1 of t, okay, plus b x2 of t. Okay, so if x3 of t is input to the system, right, what will be the output? So that's quite simple. The output will be scaled version, right? So that means if I say x3 of t right? So it will result into y3 of t, okay, and y3 of t will be equal to t times t times x3 of t. Okay, so let's check. So the scaled and some version of this one. So that means we can say, okay, so this I can expand here, so that means t. Now what is x3 of t? So x3 of t is basically a x1 of t plus b x2 of t. So this is a x1 of t, right, plus b x3 x2 of t. If I open it, I can write t a x1 of t plus t b x2 of t, right? So if you look at this one, you can easily say that it's basically the scale version of, okay, so t a x1 of t. So you see t x1 of t, okay, I can also write it a t x1 of t plus b t x2 of t, right? So I can write this is a, and if you look at this one, t x1 of t is basically y1 of t, y1 of t plus b y2 of t. So that means the system is linear, right? Because y1 x1 of t produces y1 of t, which is equal to this, and similarly this, if I sum the two and scale them by respectively by a and b, then and I say, okay, this is x3 of t. So if x3 of t is input the system, it produces y3 of t, and y3 of t equals to t x3 of t. So by simplification, you understand, right? If you look at this equation and you compare it with the top one, that is equation, let's call it, this is 1 and this is 2. So it is exactly the scaled summation of this equation, right? So that means both the properties that are superposition and scaling are hold, so we say the system is linear. Okay, so for this second case, maybe you go through it, and or maybe I explain it. Let's see. Okay, so about this example, we can we can use either property that's to tell that it's actually not a linear system, right? So for a linear system, you define that there are two properties that has to be satisfied. So that is okay, I'm using the scaling one, so that means x1 of t produces, because it's discrete time, so x1 of n produces y1 of n, right? But because we are given the values here, what the system is doing, so if you look at this one, the system is just scaling the input factor by scaling the input by a factor of 2 and adding 3 with 8, so that means y1 of n will be equal to 2 times x1 of n plus 3. Okay, so for scaling, you understand, if I scale the input by a factor of 1 by a factor of a, the output should also be scaled by a factor of a. So let's check if this happens. So we have a times y1 of n. Okay, now let me say a equals to 0, so that means a multiplied by xn will result into 0, right? So what should be the output? The output should also be 0, because a multiplied by this should equal to 0. And let's see what actually is the output. So the output is the output, right, you see, is expressed by this equation, and it says that output equals to 2 times x1 of n plus 3. Now x1 of n, because we said, is equal to 0, so if I put this equal to 0, that means 2 into 0 plus 3, so it will result into 3, right? So the first property, the property of scaling, is not satisfied, so that means we can say this system is an example of the nonlinear system, right? Because it is must that 0, if I the scaling property must hold, and scaling property says that if I scale the input by a factor of a, the output should also be scaled by a factor of a. So that means if I scale the input by a factor of a, so let's say we have a equals to 0, that means a multiplied by 0 0 multiplied by this should result into 0. So that means input is now 0. So when input is 0, output should also be 0. But if we put the value of input here in the equation, right, so we don't get 0 when input is 0, right? So when input is 0, the output is not 0, so that, right, so that means here it is not obeying the property of the scaling or homogeneity. So we say this system is basically an example of nonlinear system, because you understand it is must for a system to hold both the conditions. And what are the conditions? The conditions are the superposition and the scaling. So superposition is you add the signal and you find the output, okay, or you find find the outputs of the individual and add them. In both cases it should result into same value. So we say that the superposition holds. Okay, so in this case both will not hold. I have just tried the scaling property. You can also go for the superposition, and you will find that's also not holding the superposition. Okay, so that's all for the linear property. Now we just discuss some of the numericals on the properties we have done so far. These are the system with or without memory, stable, unstable system. Okay, so we start with the first one. So that's quite simple. You understand, for a system to have memory, the present value must depend either on past or future or both, right? So if there is no future term involved or the past term involved, then we say a system is memory less. So that's a straightforward thing. We can have an example of it, which is a capacitor. Okay, so capacitor has memory. Capacitor is a device, or we can also, in terms of signal and system, we can say that capacitor is a system that has memory, and its memory extends from -infinity up to t, right? Similarly, inductor also has memory, and in case of resistor, we say capacitor is a system which is memory less. Okay, so the second classification was whether the system are stable or unstable, right? So for a system to be stable, bounded input should result into bounded output. And how we define the bounded input? We said, okay, this is the expression for the bounded input b of x, right? So the values of x of t, absolute x of t, that means whether the values of x of t are positive or negative, they must be less than b of x. And what is b of x? It's a limit. It is the less than infinity or finite range. Okay, so if it is less than b of x, that means it's a finite, or they are bounded. So in that case, okay, so if I expand this expression, I can write x of t is greater than minus b of x and less than plus b of x, right? So x of t should have values that, whether these values are positive or negative, they must be finite, right? So b of x shows the bound or the finiteness. Okay, so this should have finite values. Okay, so again, we define that, we say that the output signal, right, if it is again bounded, then we say the system is stable, right? So for a system to be stable, we define that bounded input should produce bounded output, right? So if the input is bounded, the output must be bounded, then we say the system is stable, right? So let's look at the first equation, where we say y of t equals to ex of t, right? So what does it mean? It means whatever is the input, the system is taking its exponential, right? Do you think such a system is an example of stable system or unstable system? Because it's taking the exponential of the input, right? So again, if you look at carefully, you can go for it, and you can see that if the input is bounded, right? So if we say input satisfies this condition, that either positive or negative value of the input are bounded, finite, in that case it will result into finite values, right? So that means y of t equals to e power b of x, right? B of x. So that means this will result into or we can say that y of t, so its absolute value is equal to e power, and this is less than b of y. So that means this is an example of the bounded system, right? Or not bounded, in fact, an example of the stable system, right? although if you look at this one, you say it might result into some unbounded value or infinite value, but actually this is an example of the stable system. Okay, so we have another example, y of t equals to t x of t, right? So for any value of x of t, this will result into infinity, and y it will result in, right? So to take any value, let's consider a very simple example of x of t where it is equal to 1. Okay, so if I say x of t equals to 1, in that case y of t equals to t, right? Because x of t y of t equals to t into x of t. So if I replace x of t with 1, because that's the simplest signal, so we right, so we say x of t equals to 1, so y of t equals to t, right? So do you think it's an example of the unstable system? Right, so of course it's unstable because we say that the t values are from minus infinity up to infinity, right? So if we replace t by infinity, so y of infinity will be equal to infinity. So that means this system is basically, right, so this system is basically example of the unbounded unstable system, or although the input is bounded, right, but the output is not bounded. So it is an example of unstable system. Okay, and for the second case you can go by yourself. I think I have done the similar example while we were doing this topic, so hopefully you have the idea how to go for it. So do it and I'll check it. Maybe I ask you in the live session. The next classification we considered was causal, non-causal, and invertible, non-invertible systems, right? So let's see whether the first one given here is an example of the causal or non-causal system. So if we take the positive value here, that means if we say n is positive, in that case the value here it would be negative, right? Because for example we have n is for example plus 10, in that case y of plus 10, right? Should I write it here? Y of plus 10 y of plus 10 depends on x of minus 10, right? So minus indicate, you understand, minus indicates the past and plus represents the, okay, so that means this value depends on the past. So it seems that this will be example of the causal system, but actually it's a little tricky, right? If you take negative value, so for negative value of the y depends on positive value of the x. So positive, okay, positive you understand is future, right? And negative is past, that you know very well. So it depends on positive value of the x, that means the present value of the y, the output depends on the future values of the input. So that means this is an example of non-causal system, right? Because it's a little tricky if you look at this, right? So at first time you might say it's an example of the causal system, because you see these are the positive values. The we have negative values of x which are past, so that means it is depending on the past, right? But if you take opposite of it, that means for negative value of y n, right? For negative value of n, y depends on positive value of the positive values of the index this, right? So you understand positive value means future, right? So if you just say, you can also look at this one. So this is your time axis, right, for discrete case. So 0 means, for example, you can say 0 as your present. So these negative, you understand, these are the negative values, right? So this direction is the past, okay, and this is your future direction, right? This future. I wrote the wrong spelling, F-U-T-U-R-E, right? So future. So you can say that, okay. So in that case, you understand how it is an example of the non-causal system, okay? So if the present value you are here, and the present value depends on the future value, right, on this side. So that means this is a non-causal system, right? For a causal, it's must that the present value either depends on present or present, and past or just past. So that's fine. But if there's any term involved in the expression where it depends on the future value, then we say such a system as non-causal system. Okay, so again, there's example of the inverse system. So if a system shifts the input by amount of t naught, so we can represent it by this. You need to find the inverse of this system. Again, there's a system of the, sorry, I forgot this one. Actually, we are here now, so you understand to find the inverse side, right? So first, the system has to be invertible, right? If the system is invertible, then we can find its inverse, right? So for a system to be invertible, distinct input should lead to distinct output, right? So while doing this topic, we discussed that, for example, the squaring system is not an example of the invertible system, because distinct input does not produce distinct output. So if this is the case, then it's not invertible, non-invertible, right? So for the invertible case, the distinct input should lead to distinct output. So if we look at this example, so what is the system doing here? The system is scaling the input signal by a factor of 2. So is it invertible? Yes, it's invertible. So what will be its inverse? So we need any system that takes the input signal and divide it by a factor of 2, or you can also say scale it by a factor of 1/2. So in that case, we get the inverse of the system. So for example, we have a system, okay, this one, right? This is your input x of t, and we have a system, let represented by h, because it's performing some operation h, and it produces output which is y of t, right? This similar argument applies to the discrete time case also. And we have another system. Okay, so we just write h of -1 to indicate that it is basically inverse system. So if we cascade the original system with the inverse system, we should get the input signal, right? So for example, we have an input here, so that's resulting into, again, input this one, right? So because in this particular case, the h is doing multiplication by a factor of 2, so if I divide it by a factor of 2, I get the same. So that means at this point this was my input signal x of t, so the output signal here, it will be 2 into x of t, right? So if I input this signal to this system, it will divide by 2, so you get the original. So I hope you can go for this one. Again, this is an example of the system, that is the capacitor. So what will be its inverse system? That's quite straightforward. The inverse system of this system will be right, it will be, because you understand we represent system by the equation. So what is it doing here? If you look at this one, what is the system doing here? So the system is basically scaling the input signal by a factor of 1 by c. So in the inverse case, we will say, okay, it will scale by c. Here the system is doing what? It is taking the integration of the input signal. So what is the inverse of the integration? That is differentiation. So that means if I have system that is c d upon dt y of t, so it will result into this, right? So you can write c, what is the value of this? So that is minus that is d upon, right, dt of so what is this? This is minus this 1 by c, right, and minus infinity up to t x of ta delta. So this is integration, and this is differentiation, this is integration. These 10 cancel. This is 1 by c, this is c, they also cancel. So what you get this is equal to x of t, right? So the inverse system of the capacitor is the system that scales the input signal by a factor of c, okay, and takes the derivative of that signal. Okay, so another property of the system we have discussed was the time invariant and time variant and linear non-linear, right? So here's an example of the system, whether this system, we have to test whether the system is time varying or it's time invariant, right? So it's the system is represented by y of t equals to x of t divided by 1 by r of t. So what does it mean? It means what is the system doing here? It is scaling the input signal. Input signal is x of t by a factor of 1 by r of t. Okay, so the system involved here is a thermistor, right? So what I hope all of you understand what is a thermistor. So thermistor is a temperature dependent resistor, right? So we can say both of the signal, that is x of t, that's a time varying signal, and r of t, it's also a time varying signal, right? So we need to check whether the system is time invariant or it's time variant. So of course all of you are electrical engineering student, whether computer engineering or the electronics or power, whatever, but all of you have the idea that the value of the resistance will be different. It changes with the time for the case of thermistor, right? So this system should not be time invariant, it should be time variant, right? So to check whether any given signal system is time varying or time invariant, there's straight away two-step procedure. You take the input signal, you shift it by a factor of t, and then you apply the system. Okay, so here you shift, okay, the system, the signal, right, shift, okay, and what you get here, you get x of t minus t naught. So it introduces shift of t naught, okay, and then you find the output. So output will be equal to Okay, we represent it by for example y1 of t. Okay, I don't remember what were notations there when viewing this topic, but anyway, let's represent it by y1 of t, and y1 of t will be equal to x. What is the system doing here? It is scaling the input signal by amount of 1 by RT. Okay, so the input signal is what? It is x of t minus t naught. So this is x of t minus t naught. Okay, so this is your signal. Okay, and the system is scaling, so the system will be 1 over RF t. This is your y1. Okay, in the second step, what you do, you find the, this is shift, right? So you have the input signal x of t. Okay, and you apply it to the system. So system, okay, so you apply it to the system. So what you get here, you get y of t, and you understand. Okay, let's represent it. Okay, y2 of t. Okay, so you find y2 of t, and this y2 of t equals to what? It is equals to x of t divided by RFT, right? So you understand what is the system doing? It's scaling it by a factor of this. Now you shift this. Okay, what you do, you shift it, and you find output. Okay, let me represent the output by y3 of t. So y3 of t will be equal to what? Okay, so basically this is input to this signal, right? This is input to this system. Okay, so and what is it doing? It's shifting by what? Shifting by amount of t naught. So because they both are time varying, so it will be x of t minus t naught, okay, and divided by y of not y r t minus t naught. Why we write with this one also? Because when you shift the signal, right, the response of the system is also time varying. So previously it was r of t, now it will be r of t minus t naught, because r of t okay, let me write it like because y3t is not equal to y1t. So not time invariant, not time invariant. Okay, and you understand why it's not time invariant, because RT minus T naught is not equal to R of Ty, because at the time you find this one, it has a resistance equals to R of T, right? Now it is changed at RFT it has different resistance, and now at RFT minus T naught it has different one. So that's why it's not time invariant, so it's time varying. It varies with time. Okay, so maybe you test the following signal for time invariance. Okay, so you can go for this one, and this one. I hope you understand. Okay, these are quite clear. So that's all for this one. So maybe you do it by yourself. I hope these are quite this one I think I have already done, so you can go for this one and for this one. Okay, so maybe we end here, and we see you again in the next lecture, right? So go through all these problems carefully, right? If you have any confusion you can ask, and hopefully it will be easy for you to solve. So that's all. Allah Hafiz.